In this next video, we are going to calculate the pH of our solution after a certain amount of NaOH has been added. We are going to take a look at the strong acid versus the strong base, and we are going to take an example of 20.0 milliliters of our 0.1 molar NaOH is now added to our 100.0 milliliters of 0.1 molar HCl. So once again, we start off with our stoichiometry, and I am going to just write S for efficiency purposes. And we are going to once again write our chemical equation. HCl plus NaOH is going to yield NaCl plus H2O. Now once again, we use our modified ice chart. And so in this case over here, we're going to have our 0.01 moles, and we're now going to have our 0.002 moles, and we're going to have no NaCl and no water. Now again, if we examine the number of moles, we can see that NaOH is our limiting reagent. Therefore, all of it is going to react with the HCl. So in this case, we now subtract 0.002 minus 0.002. But in so doing, you're producing your products. So you add 0.002 on the other side, and you add 0.002 for the water. So in the end, we end up with 0.008 moles of HCl. We have no more NaOH left. We have 0.002 moles of NaCl, and we have 0.002 moles of H2O. Now, some things that needs to be considered here are the following. The first thing is we know that water is a major part of this reaction because we are working with solutions, and so therefore water is not going to be involved in any of our future calculations. The other thing that we want to make a note of is that when we take a look at the Cl, we can assume that the Cl comes from the strong acid, so it is a conjugate base. And our acid over here is our strong acid. Now the concept here is that when we have the conjugate base that comes from a very strong acid, it is very weak, and therefore it will do nothing, and we can consider it as a spectator ion. Similarly, when we take a look at our Na, it comes from our NaOH, which is a strong base. So we can consider this as a conjugate acid. Once again, because NaOH is a strong base, we can consider Na a very weak conjugate acid, and therefore consider Na as a spectator ion. So in both cases over here, NaCl is going to be considered a spectator. So Na plus is a spectator ion, as well as Cl minus, it is also going to be a spectator. Now, once we have established that, the idea here for the spectator is that it will no longer do anything else in the solution. So we don't have to worry about the NaCl, and we don't have to worry about the water. But now, when we take a look at the HCl, we now look at the next equation that it will undergo, and that is all of the HCl, because it is a strong acid, is going to completely dissociate to form H plus and Cl minus. So now we take a look at our next reaction, which is HCl. It is now going to break apart to form H plus and Cl minus. So we take a look at the concentration of the HCl. It is going to be 0.008 moles, and we divide it by the total volume. So in this case, 120 mils. So divided by 0.120 liters. And our concentration over here is going to be 0.067 molar. Because it is 100% dissociation, we can then assume that that is going to be the concentration of H plus. So now at this point, we take the pH, which is going to be negative log of 0.067. And when we put it into our calculator, we end up with a pH of 1.17. And so this is how you calculate the pH at every point of the strong acid versus strong base titration up until you reach the equivalence point. In this next calculation, we are going to be adding 20 mils of a 0.1 molar NaOH solution to our 100 mils of 0.1 acetic acid, or to our weak acid. So I'm just going to move my calculation over to the side, so therefore we can compare how the calculations are similar as well as different. So the first thing that we do is take a look at the number of moles that are being combined together, and once again we are looking at the stoichiometry of these two chemicals reacting together. So with our stoichiometry, again, we're going to be adding our acid, but this time it is going to be our weak acid. We're going to add it to the NaOH, giving you NaCH3COO plus H2O. So again, we use our modified ice chart, and we have our 0.01 moles of CH3COOH, and we have our 0.002 moles of our NaOH. And at the initial stage, there's going to be 0 amount of our salt, and there's going to be 0 amount of our water. So we are going to subtract the NaOH from the acetic acid. So once again, we recognize that we have a limiting reagent of NaOH. And so when we subtract all of the NaOH. Why we do this is because NaOH is a strong base, and therefore it wants to react completely. So this is why we do the stoichiometric reaction right now of the acid with the NaOH. And again, we get exactly the same values, which is 0.008 moles of acetic acid. We have no more NaOH left, and we now form 0.002 moles of the sodium acetate, and we also form 0.002 moles of our water. Now once again, because our reaction is taking place in water, because we're dealing with a solution of acid and a solution of base, the water is not going to be part of our consideration. Now once again, when we take a look over here, we see that NaOH is a strong base, and we also have our sodium, which is going to be considered our conjugate acid, but it's considered weak because it comes from a strong base. However, unlike the previous calculation or equation where we had the strong acid and it forms the Cl, which is the conjugate base, and we consider the Cl a very weak conjugate base, we cannot make the same assumption. Acetic acid is a weak acid, and so when it forms the conjugate base, it is considered to be a stronger base, and therefore it is going to have an effect on the subsequent reaction. So when we take a look at the Na, it's going to be a spectator. When we take a look at the acetate CH3COO minus, it is not a spectator. Because we have the weak acid and now we have formed the conjugate base, there will now be an equilibrium. So unlike before where the acid completely dissociates, our next part of this calculation is now going to be an equilibrium. And so how we write out the equilibrium is we write out our weak acid, and it's now going to be reacting with water to be in equilibrium with the conjugate base plus the hydronium ion concentration. So calculating out the concentrations of the acetic acid, so in this case over here we're using the ice chart, and it's the ice chart used in equilibrium. We're going to have our 0.067 molar acetic acid, and we're not going to worry about water. And we're now going to have 0.016 molar of our acetate. And at this point, we assume that there is no hydronium ion present. Because of Le Chatelier's principle, we know that there's going to be an equilibrium established, and there's going to be a shift to the right. So minus x over here, plus x, plus x. And now we got 0.067 minus x, 0.016 plus x, and x. Now we calculate the equilibrium using the equilibrium expression, which is going to be CH3COO minus times the hydronium ion concentration all over CH3COOH. And now we put in our values. 1.8 times 10 to the minus 5 is equal to 0.016 plus x times x all over 0.067 minus x. Now when we take a look at this again, to simplify our calculations, we make an assumption of x as being very small. Now you have to be careful here that the x's that we can consider to be very small are the ones that are adding or subtracting. So here we're going to assume that this minus x is very small. We're going to assume this plus x over here is also very small, but we cannot assume this x over here to be very small because it is being multiplied. So if we calculate it out, what we end up with is x is equal to 0.00075 molar, which is equal to our hydronium ion concentration. And so when we find the pH over here, it's going to be negative log 0.000075, and we end up with 4.12. Now, as we take a look at the two equations, we can see that the initial stoichiometric part is very, very similar. You're looking at the complete reaction of the base with the acid. However, the subsequent treatment is different. In the case of our strong acid, right over here, we see that we have a strong acid that's going to dissociate completely, and therefore it will control the pH of the solution. But in the case where we have the weak acid, what we see is an equilibrium being established. And when we see that this equilibrium is being established, what we see now is that the pH is a result of the equilibrium between the weak acid and the conjugate base. And subsequently, we have to use equilibrium expression to calculate the final concentration of the hydronium ion, and from there we are now able to calculate the pH.